Hello and welcome to a video on and probabilities, conditional probability. So in this video we're going to find the probability of one event and another event occurring either simultaneously or in succession, one after the other. And then we're also going to compute conditional probabilities, which means finding a probability under the condition that some other event has either happened or not happened. Alright, independent events. Two events are independent if the occurrence of one has no effect on the probability of the other. So and probabilities are affected by these events being independent or dependent because of the fact that they are either happening simultaneously or one after the other. And so that creates a dependency. If two events are independent, we just simply multiply because that means that one's occurrence doesn't have any effect on the other. But we're going to see later that if there is a dependency, then at least one of the two is affected by the probability of the other, or the occurrence of the other, meaning that its probability will then change. It'll either go down or go up because some event has already occurred. Alright, let's look at an example. So in roulette, a wheel has 38 numbered slots, 1 through 36, and then there's the zeros. 0 and double 0. So 18 are black, 18 are red, and then 2 are green to kind of mess up the 50-50 feel of the game, the black-red part of the game. So a ball can land on any slot with all equal probability. They all have the exact same width, the same area that they would land on. So find the probability of red occurring on 2 consecutive plays. Alright, now this means this is an AND rule. Why? Because I can, even though it doesn't say the word AND in here anywhere, I could write it as this. I could write it as the probability of red, right, red on the first, and red on the second. Alright, so I could write it as red and red. Now notice the word or does not work here. If I wrote or, red on the first or red on the second, that could be red, red, that satisfies red or red. It could be red, black, that satisfies red or red, since the first one was red. Or it could be black, red. And all of those would satisfy red or red. Okay, so it's very important that the word and is written here rather than or, because the only thing that satisfies red on consecutive plays is red and red. Alright, and because we wrote it with and, we can change that and to multiplication. That's where kind of where the and was between the two reds, and then find the probability of each one. Okay, so the probability of red occurring is 8 out of, there's 38 total, so that's our denominator, and then 18 of the 38 are red. So 18 out of 38 reduces to 9 out of 19, so multiplying the two probabilities, 9 out of 19 is 81 over 361, and then go to a calculator and get a decimal. Alright, just pay attention to how the homework wants you to present your answer. Sometimes they'll want a fraction, other times they'll want a decimal. And we start getting into these and or probabilities. Alright, so even though it didn't say the word and, this was still an and probability, and this multiplication rule applied. Alright, so you have to try to learn to see keywords like consecutive or in a row, things like that, to let you know that even though it doesn't say the word and, it still is an and probability. Alright, if two or more events are independent, we can find the probability of them all occurring by multiplying their probabilities together. So sometimes it's not just two things. Sometimes we'll have, 10 things. In this case, we have 9 things. So the probability of having a girl is a half. What's the probability of having 9 girls in a row? Well, it's the first, the second, the third, so on and so on, the 8th and the 9th. All of them have equal probability of a half, so we end up multiplying all these together. So a half times a half times a half times a half. The easy way to multiply repeatedly is to use the exponent. So 1/2 to the 9th power. Alright, now if this were different probabilities, you know, if it was the probability of a king, and then you shuffle the deck, and then a queen, and you shuffle the deck, and a spade, and you shuffle the deck, and then a red card, and you shuffle the deck, then you would still multiply them together. But it would have to be an and probability to know you're multiplying. So what's the probability of a king and then a queen and then a spade and then a red card? And you would be multiplying the whole time. Okay, so and the probabilities we multiply. Alright, so there's an in a row that lets me know that I'm multiplying this time. Alright, the probability that South Florida will be hit by a hurricane any single year is 5 out of 19. What's the probability that South Florida will be hit by a hurricane 3 years in a row, or 3 consecutive years? So there again is our key that we're using the and rule, because the probability of 3 consecutive years is hurricane and a hurricane in the next year and a hurricane in the next year. So we're multiplying. So 5/19, you could again write that as 5/19 to the third power. And again, most of the time they'll ask for a decimal, so you can kind of bypass, you know, getting this fraction right here with the big numbers in it. You can go straight to the 5/19 to the third power. You will need parentheses around this, and you get that same thing that they're getting, 0.018. So it's fine if they ask for a decimal to just multiply this straight out from the get-go without getting that fraction intermediately in the middle. Alright, now if the probability South Florida is hit by a hurricane any single year is 5/19, what's the probability they will not be hit by a hurricane in the next 10 years? So they're not hit by a hurricane at all. So this is the probability they are hit by a hurricane, 5/19. So the probability they're not hit by a hurricane is 1 minus that, which is 19/19 minus 5/19, which is, that's where the 14 out of 19 is coming from. So 14 out of 19, now they're giving us this decimal, that's for 1 year. Okay, but this is not what we want. We want for 10 years. So because this is exact and this isn't, use the fraction. Okay, always use the fraction when you're going to raise them to powers. Don't use the decimals, because that goes back to compounding error like we talked about several chapters ago. So use the fraction when you're going to put it into something to a power, if you're going to do it to an exponent. So this is any one single year. We wanted to do 10 years. Alright, and the reason why we're multiplying by itself is to not be hit by a hurricane. It's I'm not hit by a hurricane the first year, and times I'm not hit by one the second year, and not the third, and not the fourth, and not the fifth. So because of the ands, we're multiplying. So that's why we're raising it to the 10th power. Alright, I would not do this step. I would use this to the 10th power, the fraction to the 10th power, because your calculators can handle that. It's going to be much more accurate than if you use the decimal to the 10th power. So 14/19, 14/19 to the 10th power is 0.0472 roughly. Alright, and then they did 0.737 to the 10th. And they're getting 0.046. This is a little bit different. And this is 0.0473047. The 3 places ended up being the same. But you got to be careful when you're using decimals when you're raising them to powers. If you've rounded them one time, it's like you're rounding them all 10 times. Alright, 2 events are dependent events if the occurrence of one does have an effect on the probability of the other. So before, when they're independent, one happening doesn't change the probability of the other, but now they do. So when that happens, instead of just multiplying them together like we did before, notice this is now the probability of B given that A has occurred. So we have this extra piece on the end. and that adjusts the probability of B. So what we assume here is that since there's dependency, the probability of B is no longer equal to the probability of B given A occurred. Alright, which we just sometimes will just write probability of B given A. You'll see in the next coming slide that we actually write this, instead of writing the word given out, we actually write this with a little line segment, and that means given. That little line segment is read given. And this is typically the case, that since there's dependency, A's occurrence has affected B, the probability of B. So the probability of B given A is no longer equal to the probability of B prior to knowing A occurred. Alright, so let's look at dependent events. So we want a free trip to Spain, and we can take 2 people with us, all expenses paid. Bad news. 10 of your cousins have appeared out of nowhere and beg you to take them. Okay. You write each cousin's name on a card and place the cards in a hat and select one name. Then you select a second name without replacing the first card. Okay, because that person's out, you're not going to take them twice. They're not going to take up 2 seats. So if 3 of your 10 cousins speak Spanish, find the probability of selecting 2 Spanish-speaking cousins, since we're going to Spain. Alright, so the probability of both being Spanish-speaking is the probability the first speaks Spanish, the first one drawn speaks Spanish. Alright, that's the 3 out of 10. There's 3 cousins that speak Spanish out of the 10 that I'm drawing, times the probability the second speaks Spanish, given that the first one that was drawn was a Spanish-speaking cousin. Okay, well, there's 2 left, because the first one drawn was a Spanish-speaking cousin. There's 1 less than there was before, so 3 minus 1 is 2. And because I didn't put this one out, I didn't replace that name, there are 10 minus 1 in the second one. Okay, so the second one has been affected. Alright, the probability this second one, whoever this person was selected just in general, was 3 out of 10. 3 Spanish speaking out of 10. But because they're being drawn second, it gets affected. So it's gone down from 3 out of 10, which is 0.3, to 2 out of 9, which is like 0.22222. Okay, so there's definitely an effect from the first thing happening. And now the second thing is not as likely as it would have been. Alright, but we still multiply. So instead of doing this, again, I always try to reduce. So 3 out of 10 times 2 out of 9. I always try to reduce diagonally first rather than doing this. So I would do 2 goes into 10 5 times, 2 goes into 10 1 time, 3 goes into 3 once, 3 goes into 9 3 times, and then you end up with 1 times 1 is 1, 5 times 3 is 15. And you can kind of skip out this extra step in the middle where now you have to reduce that fraction with bigger numbers. It's easier to reduce fractions when they're smaller numbers, so I always try to reduce before I multiply. Alright, another one, and probabilities. This time we got 3 dependent events. So 3 people are randomly being selected, 1 person at a time. There's 5 freshmen, 2 sophomores, 4 juniors. Okay, find the probability the first 2 people selected are freshmen and the third is a junior. So the probability the first 2 selected are freshmen, we start off with 5 and 2 is 7 and 4 is 11. So we start off with 11 total, and the probability the very first one is a freshman is 5 out of 11. Alright, there's 5 freshmen, there's 11 total. Now times, the first one was a freshman, so that's the given. for the first two to be freshmen, the first one had to be a freshman, and now the second one has to be a freshman. Well, if the first one was a freshman, there's one less freshman left to be drawn for the second one. And no matter who was drawn, there's always one less drawn because we're leaving this out. Okay, we're leaving out where we are not going to give the possibility that the same person keeps going back into the group. So that's where the 4 and the 10 are coming from. And then now we're switching to juniors. Okay, so we're switching to juniors, so that's why the third one is a junior. So there's 4 juniors. All right, and then given, now there was 10 on the last draw, and we're going down 1 again because we've taken both of these folks out. But we've switched from freshmen to juniors, that's why we're not having to subtract to get the numerator. It's just there were 4 juniors. So 4 out of 9. So 5 out of 11, 4 out of 10, 4 out of 9. And we multiply those together. Alright, we can reduce 5 out of 11 times 4 out of 10 times 4 out of 9. Alright, the 10 and the 5 will reduce to a 1 and a 2. Alright, and then the 2 from that 10 will reduce with either 4. Alright, and we're left with 1 times 2 times 4 is 8 on the top. Alright, 9 times 11 is 99, and then there's only thing that both of these canceled out to reduce with the top. So 9 times 11 is 99. It's the only thing left on the bottom. So that's where that's coming from. Again, you can multiply straight across, but you do have to reduce these things when you compute a probability. Alright, let's look at conditional probability. That's what we've been doing to compute the second events and the third events. When we had these word givens in here, these second and third parts were what we call conditional probability. The probability of finding some event under the assumption or under the, with the information that some event has already occurred. So that's called a conditional probability. Find the probability that B has occurred given the condition that A has occurred. That's where it gets its name. Alright, a letter is randomly selected from the letters of the alphabet, so A through Z. And we want to find the probability of selecting a vowel. Alright, a vowel is A, E, I, O, or U. Alright, given that the letter precedes H. Well, what precedes H? A, B, C, D, E, F, G. The next letter is H. So this is our sample space. So the only things that show up there are A and E. I is after H. O and U are after H. So these are the only things, the outcomes that could possibly happen given what we're working with. Alright, so that means that our probability is just the 2 A and the E, the 2 possible vowel outcomes out of the 7 letters that precede H in the alphabet. So 2 out of 7. Alright, then you can get conditional probabilities from a table. So assuming these numbers are representative of all U.S. women aged 40 to 50, alright, find the probability that a woman in this age range has a positive mammogram. Alright, given that she does not have breast cancer, so a false positive. Alright, that's also called a false positive. So the test shows up that there is cancer or possibly cancer present, but the person doesn't have breast cancer. Okay, so what do we need to do? Well, when we have these conditional probabilities with a table, the given condition will narrow us down to a row or a column. So we'll always look after the word given, and that'll either be a row or a column, just depending on what information is given and how the table is written. So we're going to look for the column or the row does not have breast cancer. Right, that would be this column. So this is where we're looking. We're not looking at the whole table anymore. We're looking only at this column. Okay, so it's like the rest of the table doesn't even exist. It's like none of these other numbers are even there, because the condition we're given is this. Okay, it's kind of like if the people without breast cancer somehow wrote their name on a red card, right, and everybody else wrote their name on a blue card, right, and they reached in there and we drew a name out, and the name that we drew out was a red card. So it's like we knew that we're not dealing with this group of people, so we don't have to worry about anybody who wrote their name down on the blue card. It's kind of like how you can think of these conditional probabilities. So the condition has to be met, so that's going to put us into a row or a column. So find the probability of a positive mammogram. So here's positive, given that this happened. So we're only dealing with 99,200 rather than 100,000, right? So we're only dealing with this column. So this is the positive mammogram. That's 6944 out of the 99,200. So a 7% chance. All right, so what does that mean? That means, given this scenario, there's a 7% chance of a false positive using the methods that they use to detect breast cancer. That's a little bit high. I would not be I would be looking for another type of equipment if it had that rate of a false positive. But anyway, that's what we're doing here. We're using, when we have a table and a conditional probability, we use the condition to narrow us down to a row or a column. Right? Sometimes it can be row. If this said, find the probability the person had breast cancer given they had a positive mammogram, then the given condition would have been this row, and we would have highlighted that rather than this column. It's just whatever follows given is whatever column or row you're working in.